Hello everyone, today we will look our third case study which is related to pump. Here you can see the main title of case study, Shutoff pressure oversight in a new petrochemical unit and impact of incorrect shutoff pressure on downstream equipment. Let's move to the case study background. Here you can see PFD of the case study. A new petrochemical plant was under design and pump P101, a centrifugal circulation pump, was selected to move feedstock through several downstream units. One of the most critical components in its discharge line was the shell and tube heat exchanger 101, which performed essential heating before downstream processing. At early engineering stages, hydraulic calculations were performed to estimate pump differential pressure, expected operating envelope, and preliminary shutoff pressure. Based on rough calculations, the preliminary shutoff pressure was assumed to be 25 barg, and this value became the design pressure for the entire discharge system, including piping, instruments, and heat exchanger 101. At this time, the pump vendor hadn't yet provided the actual pump performance curves. Let's move to the problem statement. The case study focuses on an overpressure hazard discovered during the pump procurement. When the actual pump curves arrived, the pump's real shutoff pressure 28 barg exceeded the design pressure and maximum allowable working pressure of the downstream heat exchanger 101, which had been designed for only 25-26 barg. This mismatch created a critical safety risk. Heat exchanger 101 could fail if a blockage occurred while the pump was running. The case study examines how this pressure mismatch was identified and how the team ultimately resolved the issue by upgrading the exchanger. So my recommendation is to you, just stop video here to think a little bit about the problem itself and find solution by yourself, then continue to look the solution of the problem. In the design of new petrochemical plant, a centrifugal pump was added to circulate the feedstock through a series of downstream equipment, including a heat exchanger. They are the real industry pictures that you can see, and which was critical to the operation. The pump was selected based on process requirements. Its main specifications were made based on basic hydraulic calculations. Based on preliminary calculations, the pump shutoff pressure was considered with a 20% margin from the differential pressure, calculated to be 25 barg. This led to a design pressure of the piping, instruments, and heat exchanger in the discharge system to be 25 barg. The issue started when the procurement cycle of the pump began. The team receives the pump's performance curves. The curve revealed an unexpected shutoff head. Based on this shutoff head, the actual pump shutoff pressure was found to be 28 barg. A pump shutoff pressure here represents the actual pressure the discharge piping and instrumentation shall face when a valve is closed in the discharge line or due to any other blockage. This means that in this case, the discharge system should withstand with 28 barg. Now, based on actual pump data, the pump shutoff pressure of 25 barg, which was previously estimated, is no longer valid. So, how shall this affect the discharge system? For the piping and instruments, they had already considered a 300 flange rating, which can withstand the new 28 barg pressure. But the real issue is with the heat exchanger. As the design pressure of heat exchanger was only 25 barg, the exchanger was mechanically designed to withstand only 25 barg. Based on mechanical calculations on the heat exchanger, the maximum allowable working pressure was found 26 barg. This means that the heat exchanger cannot withstand the pump shutoff pressure in case of any blockage occurred downstream of the exchanger while the pump was still running. So now we are having a weak point in the pump discharge system. What shall we do? Adding more layers of protection seemed to be a very expensive solution. The engineering team consulted the supplier of the heat exchanger. As fabrication of exchanger was not yet completed, the team reached out to explore options for increasing the maximum allowable working pressure. The supplier offered modification in the exchanger channel, which was the weakest point in the exchanger. After a cost-benefit analysis of the supplier proposed modification, it was determined that upgrading the heat exchanger to handle the new shutoff pressure was the most cost-effective route. Once the modifications were completed, The exchanger's maximum allowed working pressure was successfully increased to 30 barg. This exceeded the pump's shut-off head pressure. The discharge system, including the exchanger pumping and instruments, was fully rated to handle the maximum pressure, ensuring process safety and also equipment integrity. This means that the whole system is now inherently safe and can withstand the maximum pressure from the pump. So, what we learned from this case study? Firstly, design pressure shouldn't be confirmed before receiving the pump curves. Before receiving pump curves, the pump shut-off pressure is considered preliminary. The final value comes from the pump supplier, so never use the preliminary value to purchase other equipment, such as heat exchanger. Finally, proactive supplier engagement matters. It means that early and proactive engagement with suppliers can provide alternative solutions that may be more cost-effective than the complex system modification. The engineering team addressed an overpressure risk through a cost-effective solution that involved upgrading the heat exchanger to handle the pump's shut-off pressure. This solution also maintained the project timeline and ensured that the exchanger design met all safety requirements without the need for additional overpressure protection measures. These are all from case study. If you have any question, suggestion, you can send your question and suggestion to our email address through Gmail, Instagram, WhatsApp. Thank you for watching our video.